Hello everyone, welcome to another class of fundamentals of particle and fluid solid processing. Today we will see the overview of whatever we have covered till now for the couple of last lectures, that this fluid particle mechanics, and specifically our interest was when the flow was around the immersed bodies. Now we have seen several things. This lecture will serve kind of a overview to the all the things that we have covered till now for this section, and it will summarize our understanding, and will at the end I will pose some question that you should think over it, and I have already answered that during my this lecture. So, the point is that the object, when there is a flow around the object, there can be two scenarios. The object moves through the stationary fluid, or the fluid flows past the stationary object. So, both the scenarios, the things can happen that we can fix a particular coordinate system with a relative velocity, where eventually the systems becomes that there is an object around which flow is happening. So, again the two scenarios are that one, let us say a stagnant or the stationary pool of liquid where a particle is falling. So, that is the example of object moves through stationary fluid, and the other scenario can be that the fluid flows past the stationary object. So, let us say there is a flat plate, we have seen this example, and wind stream is flowing over that flat plate. So, in both the cases the objective is to calculate or to understand the drag that acts on the plate or the object, how the fluid behaves around that object, how the flow behavior happens, and specific interest is to calculate the drag force. Okay. So, basically we can determine a coordinate system by defining relative velocity, so that both these systems can be determined by the problem of flow past an object. Now, the point is that, so here there is a resultant force on an immersed body due to body and surrounding fluid interaction, or the object and the surrounding fluid interactions. Now, in all the cases that we have seen till now, or in fact that all these understandings are basically based on the one of the vital assumption that the flow, upstream flow, is steady and uniform. Okay. So, if you remember the flat plate example, there was an upstream velocity of the fluid, where we have assumed that the flow is steady and coming onto the plate with an uniform velocity profile. So, this flow characteristics around the object we have seen depends on the nature of the object, that its shape, size, and other vital thing is its orientation. So, depending on that, several flow characteristics will be there, and accordingly we have to find out that what is the drag force, or how the drag force behave on that when a fluid flows over that a particular shape object. So, the forces that act on the fluid body interface are principally two type of forces. One is the wall or the surface shear stresses that on the body resulting from the viscous effect. Okay. This is mainly due to the fluid viscosity that gives us the wall or the surface shear stresses, and there is a normal stress due to the pressure. So, these two components actually contribute to the overall drag force. The drag force, when we calculate, has certain component of this shear stress drag and the normal stress drag, that is comes from the pressure. So, we say the drag which is the resultant force in the direction of the upstream velocity, and the other force is the lift force which is the resultant force normal to the upstream velocity. By typical convention, we understand that this drag force, when we say, it is the components of this shear stress drag and the normal stress drag, because remember the objects are not of a flat surface, okay? It has its curvature. Therefore, this pressure and the shear stress have its component in the direction of the flow or the upstream flow, upstream velocity. Okay. So, these two resultant force or the components of this shear stress and the normal stress, this contribute to the force that we call the drag force, and the other force that acts, that is normal to this. So, it is a kind of, if the surface is angle at a theta, the cos theta, theta with the horizontal surface, then or the x plane, conventional x plane, if the object surface is oriented like that, then you can understand that the cos theta component contributes to the drag force, the shear stresses, and the vertical component or the normal component contributes to the lift force. Okay. Now, to determine these or to quantify these parameters, there is the concept of dimensionless lift and drag coefficients. Okay. Our interest here is the drag coefficients, okay, lift and the drag coefficients. So, here we mainly focus on the drag coefficients, where the drag coefficients, if you remember, that we defined as the overall drag force per unit area divided by the rho u square by 2, where A p is the projected area in the direction parallel to the upstream velocity. So, basically shear stress contributes mainly to the drag force, okay, when the flow is in the surface is in parallel to the flow directions, and in fact it is the dominant factor. So, the thing that I mentioned, when there is a flow past a flat plate with a low Reynolds number, the viscous effects are experienced in all directions far from the plate for low Reynolds number cases. Now, here the Reynolds number is defined based on the characteristic length scale. Okay. So, if that is a flat plate, it is the length of the plate. Okay. If that is a sphere, it is the diameter of the sphere, and similar to that. So, here for the low Reynolds number case, now again remember the Reynolds number is dV rho by mu, or the inertia force by the viscous force. So, the case of low Reynolds number, that means we have very low inertia and the viscous force are dominant, and in this case it is actually experienced in all directions when there is a flow over a flat plate. And in fact, if you remember the flat for such scenario, the region of the boundary layer is basically much larger, and it starts far from the upstream point also, from the leading edge in fact. Okay. So, the thickness of the boundary layer is also high, fine, but for the high Reynolds number cases, the viscous effects influence only very close to the plate. So, here high Reynolds number cases means that there is a huge effect of the inertia, and naturally the viscous effects are less experienced over a broader region. It is mainly contained with a smaller region near the plate. This high Reynolds number cases can also be thought of like having very low viscosity. Okay. Although for real fluid there is a substantial amount of viscosity is there, but there is a flow called the inviscid flow. Okay. When the viscosity is 0, the Reynolds number is infinite, which practically does not happen, but in such cases the boundary layer, the thickness of the boundary layer or the effect of this viscous force only contains near the wall very thin layer, okay, when the Reynolds number is very high. Now, we have seen the concept of boundary layer also. The boundary layer is the scenario where fluid velocity changes from its upstream value to 0 onto the plate. Okay. So, the boundary layer has a thickness, but it is of not that much sharp interface that is available. The thickness of this layer actually increases in the direction of flow. Okay. The flow within this boundary layer may be laminar or turbulent. Basically, you can think of this boundary layer region as a region where the viscous effects are dominant. Outside this, the flow happens as if the flow is inviscid, which means there is no effect of viscosity, but that rarely happens. But this is the part that demarcates this effect, that inside that region to the near to the plate or the near to the surface, the effect of viscosity is there is velocity gradient, okay, but outside that region the velocity is nearly equals to the upstream velocity. So, there is no variation of the velocity gradient. Okay. Now, based on this laminar or the turbulent flow inside that region, this thickness of this boundary layer varies. Okay. So, then there where is the flow past a cylinder similar to the flat plate. For the low Reynolds number, the streamlines are symmetric about the center of the cylinder. Okay. So, the interesting feature is that the flow profile at the front of the spherical object and the rear point of the spherical object is nearly symmetrical when there is low Reynolds number flow or the flow is highly viscous flow, okay, or you can say the velocity is very low, okay, because this Reynolds number, low Reynolds number can be achieved by adjusting several parameters. So, in case of low Reynolds number, the streamlines across this cylinder, when there is a flow across this cylinder, the streamlines are nearly symmetrical about the center of this cylinder. But as you increase the Reynolds number, this flow symmetry ceases to exist. That means, the curvature, surface curvature, the streamlines cannot add up the surface curvature of this cylinder at the rear portions of the cylinder when it passes through a point to its upper surface, or let us say the lower surface. With increasing velocity or increasing Reynolds number, such scenario happens, and after a certain time flow separation occurs. Okay. If you remember this figure here, this C was the point of flow separation, because it cannot follow this streamlines, rather cannot follow the curved surface due to high inertia, as the Reynolds number is very high, okay, or higher and higher. As it goes higher and higher, this separation point, there is the onset of this separation point, and as it happens exactly at the rear point of this object, there is a wake formation happens. Okay. There are wakes that forms, and in fact, here the flow in this region is opposite to the direction of the upstream flow, okay, and that creates a huge pressure gradient. So, outside this boundary layer, flow behaves as if this is an inviscid flow. That means the viscosity is 0, but that does not happen. But again, the high Reynolds number can be achieved with a very high fluid velocity, okay, very high characteristic length, and similar to that. parameters. So, basically the relative importance of shear stress or the viscous effects is that you have to gauge, or you have to consider that inside the boundary region, that actually defines the boundary region, the boundary layer region, okay? Because inside that region this shear stress or the viscous effects will be there, and outside that there will be no such influence for them, okay? Now, in this case, as I said, that as the Reynolds number increases, okay, this flow separation points, okay, it is pushed back, okay, and this wake formation region, okay, it gets larger and larger. Okay, we will see that also in the couple of slides later. So, the point is, we have to understand this relative importance of shear stress or the viscous effect, okay, and that actually gives us the measure of the boundary layer. So, the boundary layer thickness in the laminar and the turbulent, both the cases are listed here, as well as the local friction coefficient and the drag coefficient value. So, these relations are what you have to keep in mind, because several problems in several questions these are typically asked, and during some calculations you have to remember these relations. So, the point is, we can see the boundary layer thickness varies with the Reynolds number to the power half in case of laminar flow, and to the power at the denominator, and here at the denominator it is 1/7. Okay. The local friction coefficient has also varied similarly, as well as the drag coefficient. Okay. So, these expressions you have to keep in mind and remember to use it wisely. Now, coming to the concept of drag, we have seen there are two types of drags. One is the friction drag, which is a part of drag resulting from the shear stress. This we have mentioned also. It is its magnitude depends on the magnitude of the wall shear stress and the surface orientation. Okay. So, it is basically in the direction that you can think of, in the direction of the upstream velocity, or along the direction of its surface. So, flat surface parallel to upstream velocity, the entire shear stress is basically the friction drag. Okay. There is no pressure drag. But on the other hand, when there is a flat surface normal to the upstream velocity, there is no contribution of the shear stress, and the overall resistance is contributed from the normal forces. Okay. Typically, this drag is independent of the plate roughness for the laminar flow, but in other cases, for the turbulent cases, it is actually in fact drastically changes. Okay, drastically increases with the plate roughness. If you remember this Moody's diagram, there you can possibly see that after a certain range of laminar so the Reynolds number value, there are the surface roughness effects are into play there. Okay. So, the other drag is the pressure or the form drag. The form drag, because it is actually comes or dictated by the shape or the form of the object. It is a part of the drag resulting from the pressure, and its magnitude is dictated by the magnitude of pressure and surface orientation, similar to the this skin drag. Okay. So, for example, in the last case that we have mentioned, when there is a flat surface normal to the upstream velocity, the entire drag force is contributed by the pressure force. Okay. And for inviscid flow, there is zero drag pressure drag on any shaped object in a steady flow. because this comes by its logical conclusion that for inviscid flow there is zero pressure drop, zero pressure drag on any kind of object when the flow is steady. So, combination of these two drag contributes to the overall drag values. Okay. So, the overall drag coefficient also is basically the skin friction coefficient, the skin drag coefficient and the pressure drag coefficient. Fine. So, if we now again come back to the problem, one problem, just to summarize the whole thing or how the things we have described, is that the wind is blowing past a 6 millimeter diameter electrical transmission line at 65 kilometer per hour. We have to calculate the drag force exerted on a 160 meter long section of this wire. So, this is a kind of overhead wire you have seen for the electrical transmission. It is of 6, let us say it is of 6 millimeter diameter. The wind is blowing at a rate of 65 kilometer per hour at a constant value. So, what is the drag force that is exerted on a 160 meter long section of this wire? So, let us say the distance between two poles of this electrical transmission line. So, here you can assume that the air density at that particular temperature or that condition is 1.22 kg per meter cube and the kinematic viscosity has such value 1.47 into the power minus 5 meters square per second. So, the things immediately that should come into your mind that okay, this we have to calculate basically the overall drag force, that is the Fd. For the calculation of Fd, we need the drag coefficient value. Drag coefficient value depends on the Reynolds number. So, first of all we have to find out the Reynolds number. Based on the Reynolds number, is it either in laminar or in turbulent or in mixed region, there are correlations or plots are available. Okay. For different shape of the object, different orientation of the flow, there are several charts, there are several tables are available. Okay. So, first object or the first task is to calculate the Reynolds number for this flow or for this problem. Okay. And then we decide, we take the value of CD accordingly and then we calculate the simple drag force. Okay. So, here the Reynolds number is calculated like this, which is velocity multiplied by the diameter divided by the kinematic viscosity. We converted this kilometer per hour to meter per second to be consistent with the units. The diameter is given, kinematic viscosity is given. So, we can see the Reynolds number comes in the range of 10 to the power 3 or 7.3 multiplied by 10 to the power 3. Now, the CD versus RE plot for this kind of let us say this is basically a cylindrical object. So, flow across a cylindrical object, if we consult the CD versus RE plot or CD versus RE drag line for this, we find that CD for this particular Reynolds number is 1.25, and then the rest of the problem is very easy, because we have seen several such examples. So, Fd is CD multiplied by the A rho v square by 2, where A again is the projected area to this flow or the area that is exposed to this flow, basically the projected area. So, here this is basically the L multiplied by the D. This is the projected area when the flow is happening across this wire, okay, where these values are also given. So, we replace those numerics and we find out that this is the force that is acting on this 160 meter long 160 meter long section of the wire. Okay. So, this 240 Newton is nearly 25 kg of weight that is hanging on that section of the well. So, this is the kind of force that is there when the wind velocity is 65 kilometer per hour and happens over a 160 meter length of the wire having a diameter of 6 millimeter. Okay. So, this is the overall summary of the things that is required for this course, and then I put these questions. This I have already answered this. If you have listened to this to the lectures, previous lectures, you will be able to understand, and you should think about this, that in flow over cylinders, why does the drag coefficient suddenly drop when the boundary layer becomes turbulent? Okay. Isn't it the contradictory? That isn't it should happen the other way around, but in reality what happens, that when there is a flow over cylinders, the drag coefficient suddenly drop, okay, as the boundary layer becomes turbulent. Why this happens? Let me give you a hint. It has to do with the flow separation point. Okay. Why the fluid or which fluid property is responsible for the development of velocity boundary layer? Okay. If you think of the concept of boundary layer and its importance, you can easily answer that. What is the effect of velocity on the thickness of the boundary layer? The effect of velocity, you can translate that into the effect of Reynolds number, and then easily you can answer such question. What is flow separation and why it happens? And is there any effect of flow separation on the drag coefficient? You should be able to answer these questions, because in the previous lectures as well as in these lectures, these answers are already given. Okay. So, with this food for thought, I conclude this class here, and we will see you with the next section in the next lecture. Thank you for your attention.